This is Shelley Physics Introduction to Kinematics Equations. Today we're going to be talking about different quantities of motion and how they work together to help us predict and also look back in time to see what's happening with moving objects. So before we do that, we need to start talking about the quantities of motion first. So I'm going to list several of those, talk about the differences between them, also provide for you their symbols and units we're going to use to describe those quantities. The first one we're going to start off with is the one that's most important to pirates, x, because x always marks the spot. So x is position. You don't move without changing your position. So x or position could also be sometimes y or r, okay? But mainly we're usually thinking about things moving side to side with a x direction of motion. Y motion would be like up or down vertically. R could be out from a circle in any direction. So sometimes we might hit on those others. You may have seen R already, talking about like the gravity law or the electrostatic force law, Coulomb's law. But position is basically unitless. It's where the object is. But sometimes we'll see it marked with X. So you can't really move without changing your position. So I'll come back to that in a moment. So X is usually a distance away from someplace, or how far something has gone, or a starting spot. So the standard unit in the metric system is meters. You may also see feet or miles. Those are all units for position. All right. So if you change your position, you've moved, you've done some motion. And when you change your position, you can measure that in a couple of ways. You can measure the distance traveled. Okay, so the distance traveled, and that is also x, but it's like an absolute value of the change in position. If you measure from one point to another and subtract, then you've got your distance. And I'll be more particular about that in a moment. So if you travel 200 miles, then your distance traveled is 200 miles. Or if I'm starting 10 feet away from a flagpole and I move forward away from the flagpole to a position of 20 feet, then I've moved 20 minus 10 is 10 feet away. 10 feet away. Distance is also in the standard metric meters. So 10 feet is about 3 meters, and if I move to 20 feet, it's about 6 meters away. So I've changed my position by about 3 meters. Another way to think about distance is with the question, how far? How far did you go? How far did that thing travel? All right, next one that's related to distance is called displacement. And let's get rid of that absolute value, because displacement is the actual change in position. So if I move forward 10 feet and then backward 10 feet, how far have I traveled? How far? The distance of 20 feet. But what is my displacement between the beginning and the end? That displacement is 0 feet. I haven't gone anywhere if I went away and then came back to the same place. Also measured in meters. So displacement is like distance and direction. The direction matters. I can move a distance of 10 feet, but I can't move a distance of negative 10 feet. It doesn't really make sense. How far did you go? Negative 10 feet. What is that? But what is your displacement? Negative 10 feet. Okay, so the direction is in the negative direction. So that displacement gives me a negative, or a direction to it, where the distance does not. So that means displacement is a quantity called a vector, and I'll come back to that in a moment. So we've hit on all the meter unit quantities. I'm going to move on here. So when we move, we can move in different ways. We can move quickly or slowly. And so what do you think this quantity is going to be? It's going to be speed. Our next quantity is speed. Now, speed is a change, a rate of change of distance. So how quickly are you changing your position? So a rate is always a change in position over time. A rate is always dividing by time in physics, when we talk about motion rates. Also, rates of energy is called power. So there's a lot of different rates. I encourage you, if you've talked about speed in a math class, oftentimes they just say rate, but it's a rate of change in position is what it is. And speed answers how fast. How fast is that thing moving? So if you take a distance divided by a time, we're taking the meter unit dividing by seconds. That's a standard unit for speed that we'll be using. Speed answers how fast. All right, our next one that's related is how fast and in what direction. And that word is velocity. Velocity answers how fast and in what direction. You'll see a parallel here, distance to displacement adds direction to it. So speed to velocity also adds direction. So speed and direction is velocity. So it's also measured in meters per second. All right. Now, velocity is also that rate, but just like distance was like an absolute value, the direction doesn't matter. There's no negative speed, so we would have to put a little absolute value there. It's like in a car, there's a speedometer, a speedometer, and it measures how fast you're going. Well, whether you're going forward or backwards, that speedometer always moves to the positive. So likewise, the speed will always be a positive number, but velocity can be negative. For example, if I'm traveling in an airplane at 250 miles per hour to the north, after an hour, I'm going to be in a very different place than if I'm traveling 250 miles to the south, miles per hour to the south. So there's a difference between that positive velocity and negative velocity, depending on the direction you're moving in. Our final quantity of motion we'll be looking at in this lesson is acceleration. Acceleration. That's a rate of change in velocity. So this is a little bit more involved. How quickly you speed up or down. Okay? If I'm speeding up, I have positive acceleration. If I'm slowing down, I have negative acceleration. Now that's if I'm moving forward. If I'm moving backwards with a negative velocity and I'm speeding up, I've got negative acceleration. My motion is becoming more negative. But if I'm moving backwards and slowing down, I've got positive acceleration. My negative velocity is becoming less negative. So what's less negative? More positive. All right, so this is a rate of change in velocity. So change in velocity over time would have units of, what are units of velocity? Meters per second. What are units of time? Seconds. So it looks kind of funny, meters per second. We can also say meters per second squared. So you'll see that transition, meters per second squared for acceleration. That was just a quick introduction to those terms. Acceleration, velocity, speed, displacement, distance, and position. Okay, those are the key terms for this lesson. All right, so where we're going to pick it up from here is just a quick little blurb about these quantities. We'll notice some of them have direction. And acceleration is a rate of change in velocity, not speed. So this one is also going to have direction. So I want to introduce to you two terms that you may hear, vector and scalar. And it's just a way to classify quantities. Vectors have direction. So you say to yourself, does this quantity have direction, or does it have no direction? Okay. So for example, I hope your life is a vector because it has direction, but I don't want it to be a scalar because, you know, living with no direction, you just kind of flounder and, you know, things don't. Anyway, I'm digressing. So what kind of quantities are vectors? What are scalars? You might ask yourself, how old am I? Well, does your age have direction? Or what time is it? Well, does time have direction? You might say, well, I heard it does. You can go back in time, right? Well, try this out. How old are you? 20 years to the left. No, that doesn't make sense. That means age is a scalar value. How about what time is it? It's 1:30 north. No, that doesn't make sense either. So time is also a scalar, just like age is related to time. They're both scalars. How about mass? Does your mass have direction? Well, I'm weighted down. Weight has direction downward towards the center of the earth, but mass does not. Mass is just how much matter do I have in my body? What is my mass? So mass does not have direction either. So now that I've been talking about a lot of quantities that don't have direction, what are some that do? Well, can I be forced forward or backward? Yeah. So we haven't talked too much about force yet in this class, but force has direction to it. There's an airplane can force itself forward with its engines or backwards. So getting back to these quantities of motion, what are some other quantities that are vectors, quantities that do have direction? Well, I talked about displacement has direction. Where are you displaced to? Where? And then we have velocity, that's speed with direction, and acceleration is a rate of change in velocity. So I can get faster or slower, moving forward or backwards. So acceleration is also a vector. Now to add those other terms to the scalars, we have distance. Distance is displacement without direction. Okay, how far have you gone? Then we've got not velocity. We got speed and acceleration. No, acceleration's already over here. It's a vector. So there is no scalar acceleration value unless you're just talking about the amount of acceleration. They're generally not really defined differently in everyday terms. Where you've probably heard it in everyday terms, possibly maybe with a car commercial or a truck commercial. Generally with sporty cars, they can go from 0 to 60 miles per hour in like 6 seconds. Or when new Teslas that are electric can go 0 to 60 in like 3.2 seconds. Crazy acceleration like that. But that's 0 to 60 miles per hour in 3.2 seconds. Or 0 to 60 in 5 would be 60 minus 0 divided by 5. So 60 miles per hour divided by 5 is 12. 12 what? 12 miles per hour per second. So after the first second of accelerating, that car would be moving 12 miles per hour. After 2 seconds of accelerating, it would be moving 24. 3 seconds, 36. 4 seconds, 48. And 5 seconds, 60. So in 5 seconds, it picks up 12 miles per hour per second. That's also similar to the meters per second we discussed in the last table. So just a little catalog of vectors and scalars. So moving ahead, I'm going to come right back to this character here. When we start looking at how objects move and their equations of motion, we're going to start with this definition. Acceleration is a rate of change of velocity. How quickly do objects accelerate? They change their velocity in a certain amount of time. So we'll start with that. Acceleration is defined as a rate of change velocity. All right. So if you're staring at that triangle going, huh, what is that? Well, this means change. It's a mathematical symbol, delta. That's the Greek letter delta. It's just a triangle. I kind of like those Greeks, you know, they're all into geometry and shapes. They even put their shapes into their letters. It's pretty cool. Anyway, change is represented by delta. And change is always a final minus an initial. So if I go from 0 to 60 miles per hour, then I've got a change in velocity. And time down here is also a change in time. So final time minus an initial time. Now, this is not looking very pretty right now. There's a bunch of these subscripts. 0 means the initial in the beginning. F means final at the end. So when you read about a scenario situation, there's always an initial and a final. The car increases its speed from 0 to 60 miles per hour in whatever seconds. So there's a start and an end. Now, I may be in a car or a vehicle and I see a deer ahead and I want to slow down. So my final velocity may sometimes be less than my initial, and that would give us a negative number for the change in velocity. So it's important to keep the final and initial and the velocities. But with time, if there's an event that's starting, well, it's always the starting time. The initial time is always, in most cases, 0. So why have minus t0 in every one of these calculations that you might do? There's not really a good sense in doing that. So we're going to simplify this to a equals final velocity minus initial velocity divided by, and we're just going to write t, the time it takes to do that, the time it takes to change velocity. And I don't like fractions too much, so what I'm going to do is multiply both sides by t. Do a little algebra here. That gives us a times t equals vf minus vo. And adding the initial velocity to both sides gives us the final velocity is equal to the starting velocity plus at, acceleration times time. And this is a wonderful place to start if you're ever talking about objects accelerating, increasing or decreasing their speed from VO to VF in a certain amount of time t. Right. This is our first equation of motion. It's going to be a first tool out of 3 we're going to be looking at. All right. Our next tool I introduced in our lab. You guys collected some wonderful data, or if you're joining us from another place, my class collected some data for an object for a car that was going down a slope, and its motion data looked exactly like this. We had some really nice data. The points lined up very well with this curve fit. See, they're a little tiny bit off. This one's a little bit lower than the line, this one's a little bit above, but it fit to this quadratic equation, this curve. And we looked at this form, y equals ax squared plus bx plus c, where x is time and y is position. So this was the format x equals, and the a term is related to the acceleration rate. X is time, so we had acceleration times time squared, plus the b is related to the initial velocity times time, and c is essentially 0. The y-intercept is 0 down here. So relating to that, our second equation we've already, oh, that's for a constant motion there. Our second equation we've already talked about. X, final position, equals initial velocity times time plus 1/2 at squared. This is our second equation of motion that we got from collecting data from an actual moving object that changed its position and accelerated in a certain amount of time. Okay, that's our second equation of motion. I'll pop our first up here also. Vf equals Vo plus A t. Right? So instead of looking at these like equations, because you've been doing math for several years, algebra and stuff like that, what we're going to do is start looking at these as their form. What kind of information are they giving us? What are they telling us about? The first one, look at it carefully. What does it have that the second equation doesn't have? Well, they both have time, they both have acceleration, they both have initial velocity. But this one reveals the final speed of an object that's accelerating. And number two, this equation reveals the final position of an object that's accelerating. So they're unique. This one gives us information, number one, that number two doesn't give us. And number two also gives us information that number one doesn't. But what do they both depend on? Well, they depend on the starting conditions and what's making them move, the acceleration. But they also depend on time. So what if I say I'm pushing on a shopping cart down a Walmart aisle and I accelerate it at a certain rate and the aisle is 20 meters long. So if I accelerate it for over 20 meters of distance, how fast is it moving? So in that question, did you notice there's no mention of time? These two equations depend on time. So can I come up with one that doesn't depend on time? So what I have here is a system of equations. And if I want to eliminate the time, then what I'm going to do is start with equation 1, Vf equals Vo plus At. I'm going to solve for time. First I'm going to subtract Vo from both sides. And then I'm going to divide by acceleration. So time is equal to final velocity minus initial velocity divided by acceleration. Now what I'm going to do is plug that in to the second equation, and this is where it gets fun and ugly. Alright, so when I do this, give myself some more room here, I'm going to get an equation without time, but then I'm going to simplify it quite a bit. And really what you need to look for here is the end result. What's the third equation going to be? And I give this to you because you are intelligent enough to do it. But I'm not going to require you to do this in class. All you're going to need is the end result. We're going to write that down and sum it up, and then we're going to use the three tools, first, second, and this third equation, to move on in this class. So all you need is the result of this, but check it out because it's some good algebra. So I'm going to plug this t value in each of these spots. So now I'm going to start with equation 2, x equals v0. Instead of t, I'm going to write this monster in there. Vf minus Vo over A plus half A t squared. And this is where it gets even uglier. Squared. Oh my goodness. Okay. There it is. Okay, that's not a 2 times x, that's the equation 2. That's what we're starting with. All right. So what do you notice at first, besides this being crazy ugly? You might notice that there's no time involved. That we've got distance in terms of initial velocity, final velocity, and acceleration. Same thing over here. So once we clean this up a bit, it's going to be looking a lot easier and more useful to use. Okay. So first thing, there's a lot of ways to do this, but I'm just going to do some distributing here. We've got a VO VF divided by A minus VO initial velocity squared, can't forget that, divided by A. And then over here, okay, I'm just going to leave this 1/2 A out front, put some big brackets in here. And what is this creature? Well, if you've ever done something like a x minus y quantity squared, you'd separate that out, x minus y times x minus y, right? Okay, put that little box over here and keep it separate. So what would I do here? I'm going to do the same thing with this. VF minus VO over A times VF minus VO over A. Squaring it. Okay. Alright, there's something going on here. I got a bunch of A's. You see that? A whole bunch of A's. So we're going to be squaring these in here. I've got some over here. So I kind of want to clean this up a little bit. If I multiply both sides by A, this whole thing over here, I'm going to have an AX, but that does eliminate the A in the denominator here. So A times VF VO over A is VO VF. And I've got a minus VO squared there. Now, instead of multiplying boop, 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 into everything here, these are all multiplied together. So this A, when I multiplied it to this big term here, is just going to turn this A into an A squared. There we go. And then we've got the VF minus VO. I haven't eliminated this A here. Okay, we're going to see what happens to that. Alright. So I got a few less brackets and junk here. So next step. Can't do much with these yet. So I'm going to rewrite those. And I'm going to keep this 1/2 here. 1/2 A squared. Alright, now you distribute this stuff on the top here. So VF times VF is VF squared. So I'm going to do that. I'm going to do this creature over here, VF times VO. But there's a negative in there, so minus VO VF. I'm putting the O before the F. It doesn't matter the way. A times B equals B times A. So VF times VO equals VO times VF. I do need to keep that negative in there. Next, I'm going to do the inner ones, VO and VF. So that's a negative VO, and another negative. And there we go. Negative VO times negative VO is positive VO squared. And then we can't forget the A squared. We'll multiply A times A on the bottom is A squared down there. So Shali, did you make this look better? That kind of looks a little more ugly, but now from this point on, it's going to simplify quite a bit. You see there's an A squared up here in the numerator divided by A squared. So those actually cancel. Yay! Looks a lot nicer. Just write everything out here again. And I've got this 1/2 character now. So I'm going to distribute this 1/2 to each of these terms as I go along. So here we go. We're going to have a 1/2 VF squared. We have a negative 1/2 VO VF. We're going to have another negative 1/2 VO VF. And a positive 1/2 VO squared. Finally eliminated all those parentheses. Alright, so do we have like terms? Can we combine like terms? Keep my AX over here for the time being. Alright, there's this VO VF and minus 1/2 VO VF and minus another. So we got a negative 1/2 minus a 1/2 is a negative 1 VO VF plus a positive VO VF. So what's 1 minus a 1/2 minus a 1/2? 0. So all these terms, these VO VF terms, eliminate. Isn't that beautiful? Okay, anyway. Then we've got a negative VO squared plus 1/2 VO squared. So negative 1 plus a 1/2 is negative 1/2 VO squared. We've got the VO terms done. And all we're left with now is this plus 1/2 VF squared. So all that junk simplifies down to this. All right. Now I've got this 1/2 term, so if I multiply both sides by 2, I should eliminate that 1/2 term. So I've got a 2ax equals 2 times 1/2 is 1, 2 times negative 1/2 is negative 1. So I'm going to have a positive vf squared minus vo squared. And now if I add that vo squared to both sides, I finally get down to what we're trying to look for here. That cancels. We get a final velocity squared equals initial velocity squared. Make that 2 better. Plus 2 times acceleration times our final position, x. And technically that's a change in position, delta x, but we just leave it as x, how far it's traveled. And this is our third equation. Now look at it, it is independent of time. It gives us the final velocity after starting with this speed, accelerating by this rate, and after we've traveled this far. So how far are we, after we've traveled this far, how fast is it going? So putting all those together, a much cleaner way to look at this. There we go. There's our acceleration equation sets. There we go. All right, so there's 3 equations. Vf equals Vo plus At. That is giving us final velocity relating to time. X equals initial velocity times time plus half At squared. That'll give us our final position after accelerating. And final velocity squared equals initial velocity squared plus 2ax. How fast are we going after accelerating a distance? Those are our tools. What are we going to do next? Well, we're going to be applying those tools and using them. We're going to take them one step at a time so you can see the usefulness of each one. So I'm not going to throw all these at you at one time. I'm not going to throw you a hammer, a screwdriver, and a saw and say, here, go to town. I'm going to show you how to use them first. Okay? So this concludes our introduction to kinematics equations. Yeah. So today's brought to you by Ender. The enemy's gate is down. Hope you enjoyed that book. Hope the English department didn't make you read it. Yeah, it could be kind of grueling, but if you ever read it on your own, it's kind of good. Yeah, just take your time on it. Fun reading that book. It's good. Anyway, thank you, Orson Scott Card.